Hello children, welcome to channel Sube. Children, today I am going to discuss question number 39 from the MCQ part of 2022-23 Physics New Syllabus paper. A uniform magnetic field of flux density capital B is directed into the plane of the paper as shown in the figure. A semicircular conducting loop of radius r rotates at constant angular velocity of omega about center O and perpendicular to the plane. The resistance of the loop is 2 ohm. What is the magnitude of current induced in the loop? Quarter omega r squared b, half omega r squared b, omega r squared b, 2 omega r squared b, 4 times omega r squared b. So children, let us try to solve this problem. Let us take a copy first of all. Enlarge it a little bit. So children, what happens when this conducting loop is rotating in this magnetic field? When it is rotating, this straight piece of the loop rotates like this. Then this other straight line also rotates like this. So it is in the region where there is no magnetic field, so therefore it doesn't influence to the current or to the electromotive force EMF. So only this conductor is generating current, because this is the conductor that is moving, cutting the across the magnetic lines. So it cuts magnetic lines when it moves like this. So therefore it generates current and EMF, electromotive force. So this circular part, this one doesn't make any voltage or any current, because it goes through these field lines, but it doesn't cut the lines. So therefore this circular part doesn't make any voltage or any current, so it doesn't affect. So we don't have to consider that one. Therefore only we have to consider this one, because this is the only conductor that cuts the magnetic lines. So the principle, what is the principle? What is the principle about this incident? Children, this one is the standard book for advanced level in Sri Lanka. This is from England. Nilkan and Parker Advanced Level Physics. So I am going to refer this book to show you. Here is the principle that we are going to use here to solve this problem. Electromagnetic induction from Faraday's or Newman's law. So normally we say Faraday's law. The EMF induced in a coil is proportional to the rate of change of flux linkage. So E equals minus K d phi by dt. So here especially Faraday says in this law, flux linkage means the flux that is being cut by this conductor, as I explained. So when this conductor rotates like this, what happens? The flux lines are cut by this conductor. Therefore that is what we have to take into account. So this circular part of this loop, when it moves, rotates, it just go through these flux lines, but the flux lines are not get cut by the conductor. Therefore it doesn't influence, only this part is the thing that is influenced to this problem. So therefore we have to consider this law. So the equation is this one. So you don't have to consider this minus sign or the constant k. K is 1. Just you can write EMF, electromotive force, equals minus d phi by dt, or delta phi by delta t. Both are acceptable. So here we don't have to use this negative sign. We can neglect it because it comes from the other law which we called Lenz's law, that we need only to find out the direction of the current. So they don't ask anything about current here, therefore we don't have to use this negative sign. Just we can write and also other thing, we are answering this multiple choice question MCQ. So here they don't check the way, the method how we found the answer. So therefore we don't have to write the negative sign. So just let us write this one, d phi by dt or delta phi by delta t. What is d phi? D phi is the flux linkage, not just flux, flux linkage. So you have to write, if they asked what is this phi, it is the flux linkage. So delta phi is equal to it is the total flux cut by this conductor in a certain time. So how to find out that? So imagine that it is rotating like this, and it wipes this area. What is B? First of all you have to get it clear. This one, B is the flux, in unit area. Flux in unit area, that means the flux in 1 square meter. So suppose there is an area like this, whose magnitude is 1 square meter. So there are flux like this, flux lines. So that one is called B. So if we know B, we can find out total flux. How? B is the flux in 1 square meter, and if we know the total square meter which is wiped by this conductor like this, so when it rotates, the total area is this one. Total area is roughly this one. So I can't let us use this tool like this. So the area is going to be this red one. Right, this right, okay. So this is the area we have to take into account. That means the area in this equation. So we have to multiply it by area, because B is the flux in 1 square meter. So if there are 2 square meter here, so we have to multiply by 2, that is the area, to get the total flux. I think you can understand like that. So the total flux is these are this one, this one, this one, this one, and all these things we have to take into account, because that is the flux linkage. When this one rotates, this conductor rotates, straight conductor rotates like this, all these crosses get cut by this line. get cut by this line. So therefore we have to take the total area that this conductor wipes when it moves in this semicircular path. So the total flux is or in other words flux linkage is B times area. So B is given, so area we have to find out. What is the area? If it were a full circle, the area is phi r squared, total area phi r squared, but here we have only half, so phi r squared divided by 2 is the area here. Right, now we know total flux linkage V times phi r squared divided by 2. So now we have to find out delta T. Now we know this part, this term we know, so let us mark it as 1. Then let us try to find out what is dt. dt is the time taken for this conductor to rotate along this place to this place, the time. If it rotated a full circle, what is the time? If it were moved a full circle like this, what is the time taken? So that is called capital T, is the period, that is for one round, but here half round, so we have to take T divided by 2, the time is period divided by 2. So now we can substitute here. E equals d phi is this one, B phi r squared divided by 2, or let's write like this, and the total thing divided by T by 2. So 2 comes here, so it get cancelled, so the remaining part is B times phi r squared divided by T, that is the EMF, electromotive force. Now there is no T in answers, omega is there, so we have to substitute omega instead of this T. So what is the equation come to your mind? Capital T and omega, what is the relationship? Omega is theta divided by T, theta divided by T, that is the basic equation. So if we take one circle, the theta is 2 phi in radian, time is capital T, the period to cover one circle or one rotation. So 2 phi by T omega. So here what we want is T isolate 2 phi divided by omega. So let us substitute here. Then what we get, T equals B phi r squared divided by capital T, instead of T what we write, 2 phi by omega, omega comes here. So cancel whatever possible, phi goes out, then the remaining term is B times r squared omega by 2, that is the EMF. Now we can leave the lesson magnetism. Now we have to go to current electricity. There you know, if there is a battery and a resistor, if the EMF is E, internal resistance simple R, external resistor capital R, current I. So you know the equation for such a circuit, E equals I times in brackets R plus R. So here now we can use this equation, because here is an electromotive force, this one also an electromotive force, but this one is chemical, but this one is magnetic. So it doesn't matter the source, whatever the source, however we have a EMF. Here also there is a EMF, and also we have a resistance 2 ohm, and also a current. What they ask is induced current. So along this loop there will be a current I. So that is what we have to find out. So let us use this equation. E is this one, we can substitute instead of this chemically. So battery is a chemical thing, so this one is a magnetic thing. So E is BR squared omega by 2. So I is what we have to find out. They have not given simple R and capital R separately. The totally they have given as it 2 ohm. So we can substitute this here. Instead of R plus R we write 2. Separately they have not given. They have given us totally the resistance is 2 ohm. So I equals BR squared omega by, we take this one to left, then go to the denominator, then 2 times 2 is 4. That means 1 over 4 quarter. The order is omega RB order, they have written omega RB. So this is the I. So let us now select the answer, this one. What is the first one? I think quarter omega R squared B. Yes, first one is the answer. So let us check the answer sheet. The question number 39. 1 first one is the answer. Okay, so we have successfully solved the problem. So I think you understood. It is not difficult actually. These types of questions, there are a lot of questions in past papers. If you referred, you can find out lot of past paper, lot of same type of questions in past papers. This is a common question, so it is not therefore easy, it is not therefore difficult, it is very easier. So what we used, Faraday's law, and also the simple equation for simple ideal circuit in current electricity. So if you know these two equations, and if you have the idea about these equations, how to use them, you can easily you would have easily answered this question. So children, I think you understood, I think you are happy. So now I am going to give you some target questions as usual. So children, I made this target question number 1 for you. I altered the question. So now you can try it honestly. Pause the video first of all, and then start. So children, as you pause the video, now I am going to start. So children, there is a short method since we have done the first question, otherwise you have to start from the beginning itself. Since this angular velocity omega is the same, not changed, the EMF must be the same as in the previous question, and also this resistance of the loop is the same as in the previous question. The current must be the same. Therefore, since you have solved this first question, now you don't have to solve again. You can choose the same current. So this one and this one, quarter omega R squared B. This current, the same current should be here, because the omega is same and also this resistance is same. Since omega is same, the EMF is same, and also since this resistance is same, the current also should be same. But if you are not satisfied, if I solve that question that way, so I am going to show you all these things. E equals delta phi by delta t, that is Faraday's law. So what is going to be delta phi? B times area. So area, what is the area? Area is the area that we have to find out when this piece of conductor is moving from here to here to here, because at that time when the conductor is here, the other part, the other straight piece, this one is still in the outside, not entered the magnetic field. So if it entered the magnetic field, the question is complicated, then there will be no current. So I am not going to explain all these things because I have no much time. So therefore I take only this quarter, because in that period this other straight wire is outside of the magnetic field, so that so it doesn't influence the final result. So therefore I use the locations of this piece of wire from here to here only, but you can use this total semicircle even, but it will be complicated. So I am going to solve this question in the simplest way. So from here to here you can consider, since in this portion that the other straight wire is out of the magnetic field, so it doesn't influence the final result. So this is the wire that generates EMF or current. So what about this curved part, curved section? It doesn't make any current. It doesn't make any current even though it is in the field, because since this curved section does not cut the magnetic lines of force and creeps, just it creeps between these magnetic force lines without cutting them. So therefore no electromotive force is induced in the curved section. Again I am saying, since this curved section does not cut the magnetic lines of force and creeps between them, no electromotive force is induced in the curved section. So therefore we have to neglect this part and this part. Only we have to consider this piece. It is moving, rotating from here to here. So what is the area get cut by this line? Quarter circle. That means we have to write here as area, for area, phi r is squared divided by 4. If it were a full circle, it should be phi r squared, but since it is quarter only, then divided by 4. So here we write it b phi r squared by 4. Then what is delta t? If it were a full circle, like this, what is the time? Capital T. But we are considering only this quarter, so capital T divided by 4. So substitute here, then 4 cancel, b phi r squared by t, that is the EMF. So T equals what? 2 phi by omega. So substitute then b phi r squared, T is going to be 2 phi by omega. So phi cancel, then E is b r squared omega by 2. So now the equation for ideal circuits, E equals I times R plus R. That is in the lesson current electricity. So instead of this E we write b r squared omega by 2. So current we need isolate. So this total part is 2 ohm. It has been given, and previously we used given. So it comes here. So b r squared omega divided by 4. So that is the same answer, quarter times b r squared omega. So that is the first and second answers, this one. So that is why I said that since this omega is the same and resistance is the same, we don't have to calculate again, just we can directly select these two answers. So now children, let us try to find the direction of the current. There must be only two directions, either from P to O or O to P, because this part, this section of the loop only is making EMF or current, induced current, generating only this one only generating current. So we can use two methods. There are two methods. So one is called Fleming's right hand rule. The other one is called Lenz's law. But we have to get help from Fleming's left hand rule there. So let us first try this first method, Fleming's right hand rule. So we know that only this part of the loop is making EMF or current. So therefore we don't have to use this arrow we need. These other things we don't want. But actually yes, if we are going to use this second one, we need this part. So we are going to now try this first one. So we know the direction of motion, this way, motion. In Fleming's right hand rule, what he says is, if we pointed our index finger to the direction of flux density B, that is into the paper now, like this, and if we pointed our thumb, first of all you have to arrange these three fingers, that means thumb, index finger and center finger, mid finger, perpendicular to each other, that you know, don't you? So after doing that, you have to direct this index finger towards the direction of the B, flux density, and you have to rotate your hand without changing your fingers, so that the thumb is directed to the direction of the motion. Since we know the direction of the motion, we can do this. So like this. So after doing that, we get the direction of the current from the mid finger. So this one is the right hand. You can identify this right hand. So let us place here. So like this, the direction of the motion shows from the thumb, and then the index finger into the paper, and mid finger shows the direction of the current. So very simple. So now we know the current is towards this way. So for the simplicity, I deleted all these other parts, but if there should be a current, there must be this the loop must be closed, otherwise there will be no current. So I deleted only for you to easily understand that. So now I have to draw this part, because if I mark the current, if I consider the current, this deleted parts also should be here, otherwise there will be no current. You can't get a current alone straight wire like this without having a loop. So now this is the final answer. The I is from P to O using right hand rule. So the answer is this one, first one. So now I am going to show you So now children, let us discuss this second method using Lenz's law and Fleming's left hand rule. So what is Lenz's law? So Lenz's law is this one. The induced EMF is in such a direction that if the circuit is closed, the induced current opposes the change of flux. So that is why I said that the circuit should be closed, otherwise we can't talk anything about current. The circuit, suppose the circuit is like this, broken from somewhere, so can any current flow along this? No, current can't flow along this because the circuit is broken. So that is why he says that if the circuit is closed, then we can talk about the current, otherwise we can't. Only we can talk about an EMF even though the circuit is broken. Even though the circuit is broken, we can discuss about EMF, but we can't discuss about current if the circuit is broken. So what is this word? Opposes. The current opposes, induced current opposes the change. So since we know the direction of the motion of this conductor, because only this one is making current, making EMF, and after that current, since the loop is closed. So direction of the motion is towards left. Motion is towards left. Motion. So then there will be a current this way or this way. We don't know the direction from P to O or O to P. However, there is a current. So when that current flows, what happens? It opposes. It opposes means it generates a force opposing this motion. Opposing means to the opposite direction. To the opposite direction there will be a force generated by this induced current. So this force now we know, since it is opposite, so we can mark it like this. Since we know this the direction of the motion is to left side, and the opposing force must be towards the right side, like friction. So this is a magnetic force. This is a magnetic force because there is a magnetic field here. So where did we learn about magnetic force? You must remember F equals BIL equation. When we were learning at the beginning itself of this lesson, magnetic fields, this equation we learned, and also we learned left hand rule there. Whose left hand rule? Fleming's. Fleming's left hand rule. So that is what we are going to use to support this Lenz equation. Since we have now found this opposing direction, now we don't want Lenz rule. That is what we get from Lenz rule, this word opposing, opposes. So let us delete that. So now let us get help of this Fleming left hand rule. So Fleming's left hand rule, we have to find out where I have placed this left hand. Somewhere it must be here, left hand. So now we take the left hand, because already we know, we have learnt that about left hand already when we were learning about this equation. So what is the rule? First of all, we have to set our three fingers, thumb, index finger and mid finger, perpendicular to each other, and then we have to direct the index finger towards the direction of flux density B. Then we have to turn our hand without changing the set, these three fingers, the thumb towards towards the direction of force. There is no motion, only force. Then the mid finger shows the direction of current, that we don't know. So let us do it now. So let us take this left hand. This one is left hand, remember. Already we know the direction of force, that is towards right side. So like this. So now the direction of the current is towards downwards. Down. Understood? Yes. So now we can mark current this way from P to O. So don't get confused. If you are using Lenz's law, you have to get help from this Fleming's left hand rule. In that rule there's nothing about motion, only there's a word called force. If you are using left hand, right hand, there is a word motion. Thumb denotes the direction of motion. If you are using right hand, you don't have to get help from Lenz's law. Alone this right hand rule, you can get the answer, direction of the current. So if you are using Lenz's law, you have to get help from Fleming's left hand rule. So now I think without getting confused, you have to keep these two separately in your mind. So now we have found the answer. So still it is the first one from P to O. So now children, I think now the time is to wind up the video. So I think you understood this. I think you are happy. So children, now I am going to wind up the video. I think you are happy. So I have to sing the same song as usual. But if you are happy, you have to make me happy too. How? By subscribing my channel. So I request only those three things: subscribing my channel and liking my video. Otherwise YouTube will push my video somewhere to a corner. And also share my link among your friends. I think you are not jealous, I think you are generous. You like your friends also come to your campus. So therefore share my link among your friends. For those who have done already, I must thank you very much for watching my videos, and thank you very much for subscribing my channel, and also thank you very much for liking and sharing my link. So children, let us see you tomorrow in the evening at 6 o'clock. Goodbye.